What I want to talk about today is parametric representations for some of the functions that we would extremize or optimize inside a functional. So let me just remind you where we've gone thus far. So thus far we've developed variational solutions, assuming that the dependent variables were single-valued functions of the independent variables. So if you remember back to when we were extremizing functions that were subject to constraints, and we had something that looked like something running from, let's say, a down to minus a, right? And we said, well, there's a function here, right? We said this was u of x. Of course, this is only a function u of x if it passes the vertical line test. If it's a one-to-one function. And we said at the end when we came up with our solution that the solution that fixed this length and then maximized the enclosed area around the x-axis was the equation of a circle. And we said that it required some additional discussion to talk about thinking about parameterizing solutions in such a way that we could admit easily non-one-to-one functions. And we also noted that even though we had assumed single-valued functions, the solution that we got was correct. So we want to address some of those concerns today. So the key feature is that when we extremize a functional, the Euler-Lagrange equation may yield a solution that's not single-valued. So how do we handle this? So what we're going to do is, in what follows here, we're going to eliminate the restriction of single-valuedness by considering a parametric relationship where, for example, let's say that x is some function of a parameter we'll call t, and u is also some function of a parameter that we'll call t, right? So those can be varied separately and independently, which allows us to handle the problem of single-valuedness. So with that in mind, let's re-examine our classic functional. Right, so we've been working with this functional most frequently. I of u is going to be equal to the integral from a to b of f x u and u prime dx, right? Let's call that equation 1. We're going to want to re-examine this functional as to the requirements of single-valuedness. Okay, so what did we have previously when we did this? We had the Euler-Lagrange equation given as follows. Partial of f with respect to u minus d by dx times, or rather of the partial of f with respect to u prime equals 0. Let's call that equation 2. That's the conventional Euler-Lagrange equation. So now, instead of assuming that u is a function of x, let's express x and u in standard parametric form. So we're going to say here that x is some function of t, where t is our parameter, and u is a function of t, where t is our parameter. Okay? And we'll collectively call these equations 3. So what we want to ask is, we want to find out how this representation affects the functional given by equation 1. So we're going to observe a couple things. First, if we take the differential of x in equation 3, we end up with something that looks like dx is equal to, now this is via the chain rule, it's going to be dx dt times dt, right? Which we could just write as x dot dt. Okay, so let's call that equation 4. Similarly, we can say something about u prime, right? Where we would say then that u prime, which we know it to be du dx, we'll be able to write as du dt over now dx dt, right? I have not changed anything there, which I could write as u dot over x dot. Okay, let's call that equation 5. So I can substitute equations 4 and 5 into equation 1, that functional, to get the following. We end up then with I is going to be equal to, now we're going to integrate over t, so we're going to go from t1 up to t2 of, now f looks like x u, and u prime we just set up here was u dot over x dot. And then dx, we said in equation 4, was x dot dt. Okay. And of course, we have those endpoints where now x of t1 equals a, and then x of t2 is equal to b. Okay, let's call that equation 6. So now we're going to call that integrand a new function. So let's define a new function. Let's call it g of x u x dot and u dot, right? And that's going to be equal to f of x u u dot over x dot times x dot. Let's call that equation 7. So substituting equation 7 into equation 6, we can rewrite the functional as follows. So now we have a functional I that's a function of two dependent variables, x and u, is going to be equal to now the integral from t1 to t2 of g x u x dot and u dot dt. Okay, let's call that equation 8. So what is this? This is a functional with multiple dependent variables. We've already covered in this class how to handle that. So we can write down the Euler-Lagrange equations directly. Right? So in this case, those dependent variables are x and u in this case. Okay, and the Euler-Lagrange equations are that partial of g with respect to x minus d by dt partial of g with respect to x dot is equal to 0. That's one of the equations. The other is the partial of g with respect to u minus d by dt partial of g with respect to u dot equals 0. So those are our two Euler-Lagrange equations, and we'll call those equations 9. Okay. So the equations shown in equation 9 are a valid set of equations for the parameterized problem. Okay. However, if you think back to our isoparametric example, we showed that using equation 2 still produced a valid extremizing solution. And in fact, this wasn't necessarily a single valued function. So again, equation 9 is all well and good, but how do we reconcile the fact that equation 2 got us a solution as well? There are certainly cases where we would just want to begin with equations 9 and proceed with the solution. But we want to understand how equation 2 still produced a correct solution and how we can reconcile this. So that's the question we want to answer now. So what we're hoping comes out of this is that equations 9 lead us back to equation 2, right? If everything is if everything is consistent. So let's go ahead and consider the following. Okay, number 1. So how about from equation 7 we can define the partial of g with respect to x? we say the partial of g with respect to x is equal to the partial of f with respect to x times x dot. Right? And all that is taking the partial with respect to x of equation 7. Okay? Now how about a second consideration? So now we're going to look at equation 7 and in conjunction with equation 5 and look at what's the partial with respect to of g with respect to x dot. So we would say then that the partial of g with respect to x dot is equal to the partial with respect to x dot of the quantity, this is equation 7 that I'm writing out here, of f x u prime times x dot, which will end up being f times the partial of x dot with respect to x dot, which is just 1, and then plus x dot now times the partial of f with respect to, we know that there's an x dot dependence in u prime. So we'll say partial of f with respect to u prime, that's just chain rule. Partial of u prime with respect to x dot. Right? And we know what the partial of u prime with respect to x dot is, right? Because u prime is given as u dot over x dot. So we can write this as f minus x dot partial of f with respect to u prime times u dot over x dot squared. Okay? So let's continue on simplifying. And this now becomes f. I'm going to multiply x dot times 1 over x dot squared to end up with f minus partial of f with respect to u prime times now u dot over x prime, or sorry, x dot rather. We know what u dot over x dot equals. That's u prime. So this finally comes out to be f minus partial of f with respect to u prime times u prime. Let's call this, let's go back here and label these. This is equation 10, and this is equation 11. Okay? A couple more observations. Okay, number 3. Okay, from equation 7 again, we can compute the partial of g with respect to u. And that's going to be equal to the partial of f with respect to u times x dot. Let's call that equation 12. Okay, and then let's look for a fourth. We want to look at partial of g with respect to u dot. That's again from equations 7 and 5. And so we end up with partial of g with respect to u dot is going to be equal to, just from equation 7, x dot times the partial of f with respect to u dot, right? But what do we know? We know that the partial of u prime, this is just from the definition in equation 5, is equal to 1 over x dot times the partial of u dot. Okay, and that implies that the partial then with respect to u prime is equal to x dot times the partial with respect to u dot. Okay, so we can continue on the process here and say that the partial with respect to u dot is equal to 1 over x dot times the partial with respect to u prime. Okay, so combining this, so thus we can write that the partial of g with respect to u dot is equal to x dot now times the quantity of 1 over x dot partial of f with respect to u prime. Right? x dots cancel out, and we're left with partial of f with respect to u prime. Let's call this equation 13. Okay, in order to make our substitutions, now we need to differentiate equation 11 with respect to the parameter t. So that'll be observation 5. Okay, so we differentiate that with respect to t, and we end up with d by dt of partial of g with respect to x dot is going to be equal to now d by dt. We're just making that substitution that we already computed. This is f minus u prime partial of f with respect to u prime. Okay, we're also going to make a similar jump. Let me kind of show you where this comes in. Okay, so what happens at this equal sign? So remember from equation 4. So from equation 4, we had that dx was equal to x dot dt, right? Which means that d by dx is equal to 1 over x dot d by dt, right? And therefore, that d by dt is equal to x dot d by dx. Okay? So if we make that assumption, then this becomes x dot d by dx now of f minus u prime partial of f with respect to u prime. Okay? So now, let's go ahead and keep dropping down. What else does this equal? I'm going to now carry out the differentiation. So I have that x dot term still in the front. I'm going to draw a set of braces here. And now I take my derivative with respect to x. So this becomes the partial of f with respect to x plus the partial of f with respect to u times du dx, which is u prime, right? Plus the partial of f with respect to u prime times du prime dx, which is u double prime. Okay, so that's differentiating just f. Now I take the derivative of the second term there. So we have a u prime times a del f del u prime. So we're going to use the product rule on that. So this becomes minus u double prime times del f del u prime. And then we'll have a minus u prime times d by dx partial of f with respect to u prime. Okay, I know that's a lot of terms. Some of them are going to cancel. Obviously, these middle terms cancel, right? And what we're left with is equal to x dot, here's our brace, partial of f with respect to x, plus we have this u prime we can factor out, so u prime now, partial of f with respect to u minus d by dx partial of f with respect to u prime. Okay. We'll just leave this there and call it equation 14. I'll just point out, you'll notice this term here is precisely the Euler-Lagrange equation of equation 2. Okay. So we'll make one final observation. We'll call it observation 6. Okay. Similarly, we can do the same thing with d by dt of partial of g with respect to u dot. And we can come up with the same thing. It looks like d by dt of the partial of g with respect to u dot is going to be equal to x dot d by dx of partial of f with respect to u prime. Okay, call that equation 15. Okay, now what we're going to do is we're going to substitute all of that back into equation 9. So substituting 10 through 15 into 9 gives the following. We have then that partial of, this is the first equation, partial of g with respect to x minus d by dt of the partial of g with respect to x dot equals 0, right? That's the first equation of equation 9. If we make our substitutions, we find that that now equals partial of f with respect to x times x dot minus x dot times the quantity partial of f with respect to x plus u prime times partial of f with respect to u minus d by dx partial of f with respect to u prime. Close our bracket there. So that's the first equation. Let's do some simplification. You can probably see already that this partial f with respect to x times x dot cancels out with that first term there, and we're left with the following term, which is just x dot now times, there's actually a negative here, times u prime times our conventional Euler-Lagrange equation, partial of f with respect to u minus d by dx of partial of f with respect to u prime. Okay? And I'll just remind you that that equals 0. So what does this mean? Well, it means either that x dot and u or u prime equals 0, right, which are effectively trivial solutions, or this quantity here equals 0. So the implication from this first equation, partial of g with respect to x minus d by dt of partial of g with respect to x dot, the implication there is that that leads to the Euler-Lagrange equation given in equation 2. Partial of f with respect to u minus d by dx partial of f with respect to u prime equals 0. So let's call that equation 16. Okay, so that equation led to the Euler-Lagrange equation. What does the other equation lead to? Okay, that second equation in equation 9 looked like partial of g now with respect to u minus d by dt partial of g with respect to u dot. That equals 0. So let's make our substitutions now. That first term looks like partial of f with respect to u times x dot, right? And then we have a minus x dot times d by dx of partial of f with respect to u prime. Okay, let's factor out the x dot. And we now have partial of f with respect to u minus d by dx partial of f with respect to u prime. Again, reminding you it equals 0. So either x dot is equal to 0, again, which is a trivial solution, or this thing in parentheses is. And so it, in fact, also leads to the Euler-Lagrange equation, which is partial of f with respect to u minus d by dx of partial of f with respect to u prime equal 0. Let's call that equation 17. So let me write down what I just said. We observe that both 16 and 17 are the same Euler-Lagrange equation as given in equation 2. So effectively, they're yielding equivalent solutions. And so what we can conclude that any relationship that satisfies the Euler-Lagrange equation in equation 2, and that means that's any relationship single valued or not, is going to be a valid extremizing relationship for the functional given by equation 1. Okay? So the upshot is sometimes you want to frame your extremization or your optimization problem in the form of equations 9. where you're going to explicitly get that parametric dependence. But even if there happens to be a parametric dependence, if it isn't a true function or one-to-one function like we saw with the isoparametric problem that we did an example for, that solution that we obtained from the equation 2 is still valid. And that was what the sort of everything after equation 9 up through equation 17 was demonstrating, was that those solutions are in fact equivalent.